Hello, this is Andre again. Today I'm not talking about a hardware topic, but a software topic. I noticed I haven't talked about my GeckOS operating system on an official video on that stream, only in a very old one, before I started counting episodes. So if you want to know more about my multitasking operating system with internet support for the Commodore 64 and other 6502, stay tuned. Hi there. So today I'm going to talk about my multitasking operating system for 6502 computers. What I've done in the past, what is the current state, and what's the outlook for the future. So multitasking on the 6502, you might be asking, does that actually work? Because that's a challenge. You have only fixed addresses for stack and zero page. There's no position independent code and you have no memory protection. So, but I did it. Some other people did it too. I'm not the only one. I'm not the first one, but probably the only one that has such a lineage from the past, really. Until today, with a maintained operating system. So when did that happen? When did I start it? If you look to the past, 1985, there was Windows 1, then we had Minix. In 87, 1989, Windows 2.11 was DOS shell. Then 1991 came Linux. And then there was this discussion about Windows 3 point something is still just a DOS shell and it's cooperative multitasking. And in 1993, Microsoft brought out Windows NT with the first consumer market operating system with preemptive multitasking. Yeah, I was before that. In 1989, I started my initial Commodore PET clone with a memory management unit, and in 1990 I had version 1 of my preemptive multitasking operating ready. So what was that originally built for? Where did I come from? You can see here, this is a picture of not the but similar version of the 3032 Commodore PET that I started programming on. And then I learned at school, when I left school, or later at school, when I got my Commodore 64, yeah, those games that I love to play on the PET don't work on the 64. So in 1989, I built the first replica based on Euro PCBs. So on the right hand side, you can actually see a picture from early times, one of the earliest pictures I did from that system. You can see it's all on perf board with manually with each wire soldered separately onto a backplane here, and you can actually see here this is connected to my Atari ST, which is running as a disk server. And this is on the left hand side. There's a more modern version with produced PCBs, but still those are the days when even the protective coating was expensive, and I left it. So you see this has a history, and you can see my other videos on all my PET clones, and you can watch and learn more about those in these other videos. So what was the specifics that this GeckOS operating system 1.0 was made for? So it was a 6502 processor. I could use NMOS or CMOS. I had an MMU, memory management unit. I'll talk about more in detail on the next slide. But it was translating the upper 4 address bits of the CPU into 8 address bits. So it extends the 64K of address space of the 6502 to 1 megabyte physical address space. And it does so in 4K blocks of 4 kilobyte that you can, each of the 16 blocks in the 6502 address space, you can map to any of the 4K blocks, of the 256 4K blocks in the 1 megabyte address space on the bus. A video card using CRTC compatible to the pad, not exactly in the beginning, but later it got better, especially with the I/O. It got more compatible. It got an RS-232 interface, and it's all lots of I/O that is now available on Euro PCBs, and I have a link in the description below where you can find all the PCBs for that. So, but this was the original specification that this operating system was made for, and the MMU played a prominent role. Because what it made possible is you could map different processes in memory, and each process or task, as they are called in GeckOS, has its own 0-page and stack. So it was just totally easy. You could just give a task 4K of RAM, and it would get any one of those blocks in the physical address space mapped to its 0-page RAM, and then you had 3.5K of program space basically available. Or you could, of course, map more than just one page. You could have multiple pages, and depending where the memory was actually available on the physical address space, you could map that from there. So that was the general approach. This provided some kind of memory protection. The MMU did the address translation, and on every context switch between processes or tasks, the MMU would be loaded with a new set of configuration for memory. So how did GeckOS work internally? How was it structured? It was actually structured in a rather modern way. It was done as a microkernel that was basically there to facilitate the inter-process communication between processes like file systems, shell, monitor, other processes, and devices. And this in the middle here is the kernel. It consists of a device feature, device communication, so you can use them. Environment is the feature that switches between the different memory settings, memory configurations in the MMU. File system manager is actually one that just enumerates the different file systems. I'm going to show that later. So when a shell wants to open a file, it goes to the file system manager and say, okay, I want to go to drive 2. And it knows, okay, drive 0 and 1 is in this fsdef file system task. Drive 2, 3, 4, 5 is in that fsiec file system task. And the next two are in the fsibm, or actually FAT floppy disk file system. I should rename that actually. And the kernel then actually switches between the tasks in a preemptive way. So there's a timer interrupt, and once a task gets interrupted, it returns into the kernel. The kernel decides should it be running, should it be switched over to another task, and the task can of course also yield the CPU to any other task when it knows it doesn't have anything to do. The stream module here is for the intercommunication. So any kind of communication between tasks and file system is you put a byte into a stream on one side and then you take it out on the other side. And that works with devices, works with tasks, and so on. The memory setup is then to manage the physical memory. So that was the first version of GeckOS, and further milestones. This the system can work as a disk drive for Commodore PET or Commodore 64. So you can use the disk drives, the file systems in GeckOS as disk drives on a C64 or PET attached to the GeckOS machine on the IEEE 488 bus for the PET or the IEC bus for the C64. There's a standard library called Lib6502, which is very nice. It even provides networking support if there is a special task running in the background that actually does the TCP/IP communication or whatever kind of networking is being enabled. Actually, there is a TCP/IP implementation. You can do a remote login. You could use. The last test showed it was broken on somehow, but yeah. I'll see if I can demo it. There's a web server. You can use a server on the internet to load files from. It's a file system task like any other of the file system tasks. And there's a World Wide Web server, an HTTP or better HTTP server. No HTTPS. It's only 1.0, and the best way is probably today to telnet into it and submit the GET from the telnet telnet line from the console. Also this Commodore 64 is supported, which is very interesting, and also the original PETs are supported now. And this works because I have refactored the kernel such that it doesn't need to remap all the memory, but it can share zero page and stack. There are options in the stack. You can copy the used part of the stack every time on a context switch, or you can have the stack, the one page 256 bytes of stack separated into areas for each task. However, that limits the number of tasks you can actually run. Also, have a relocatable file format. So binaries you load into the system are automatically relocated to where enough free memory is, and are run from there. Also, there is a dynamic linking. So the kernel, depending on the architecture, can be at any address. So for example, on the original PET, you cannot remove the kernel ROM. So you cannot put the kernel of GeckOS somewhere in the upper half of the address space. But the binaries that are loaded have an undefined label, and this is being resolved while loading. So it's late binding is implemented as well. And that also allows to all that stuff, relocatable file format, you can run the same binary multiple times at the same time in the operating system. So what features are there? We have, as I said, we have preemptive multitasking, priorities, multi-threading. We have virtual consoles, signals and semaphores. The shell can do backgrounding, redirecting, piping. There are environment variables. It's using a standard library, Lib6502, which is also being used by Linux as a source compatible version. You need to use the cross-assembler XA64, which incidentally I also started in '89, and the 065 relocatable file format. So today it supports the original CSA architecture with the multi-card system. It supports and MMU. It supports the Commodore 64. It supports the 32K pad, but due to the limitation in memory, it's really just a technology demo. What I recommend if you want to test it out on an emulator, I recommend you use the 8296 Commodore PET. That's very nice because it has 80 column display and it has 96 kilobyte of usable memory. And that is what I used with bank switching and so on to run some system programs in one bank and user programs in another bank. So, demo time. So, let's start the demo with the on the Commodore 8296. You load the loader and run it. You can use auto start on device emulator, but yeah, just for the sake of showing it here, I'm doing it manually. It loads the so-called boot image or init ROM image, which contains a basic set of tasks that are being run, which is the init process and some file systems, and could also have another kind of shell like we see here. And this is now one that is not in the boot ROM image. This is loaded from disk when booting, which we can see here on the red light on the emulated disk drive. And there we go. Here we are. So we have some commands like uname. We can see all the processes, and as I said, this operating system is not only multitasking, it's also multi-threading. You can see here that this is the task information. Then there is the second line that has the thread information. For currently there's only a single thread per task, but you could have multiple. And you can see the init process is paused, but the task is ready. But pausing means it's going to be woken up when it gets a signal, and it gets a signal when a child dies. And when the child dies, like, okay, this is a typo, so it will not find the command. But if a child dies, like the shell, it automatically starts the shell again, because the shell has been started with restart configuration within it. Then there we have the file system, fsdev, fsiec for the devices, and IEEE 488 disk drives. And we can see that if we go to LSA, you can see, okay, just wait, give me a sec. So you can have, you can see the devices. Actually, this is, you can also do some long format, because that shows actually the devices is the name. And then we have 4 video devices and a null device, a spooler, and that's it. On the Commodore 64 you would also have a serial device. So we have 4 video devices, and when you look at the process table again, we have file system device, file system IEEE, and we have shell, and we have another shell, and we have PS. That's actually the program here that we run here. Yeah, where's that? When I press Shift Tab, I get into the second console, and here I have another shell, which is actually the old shell from GeckOS 1, which is going to be moved into some kind of debugging tool and not into a full shell anymore, because the other shell here is much more modern, is the actual maintained one. So and then, oops, typo. Let's see what I'm not warping. So this is basically the original. So LSC basically is the disk drive that is the default here, and you can see here this is already content of the disk drive, and there's a lot of documentation. Going to show some of the documentation later as well. So let's see what we have when we look at the memory. So this is actually, this is the memory chain, which is very, very detailed. I forgot actually I wanted to go into this one to show the memory map. You can see the different tasks which are here at the shell, and the LSMem is the actual program here itself. You can see how much memory they actually use. You can see here each task uses 2 memory blocks. One is approximately 2 blocks, and then we have the shell, which is 5.5 K, and the LSMem is a bit more than half K. And if you look at the memory map, you can see there is some used area for the system in the beginning. There's part for the kernel in the end, and then this is all program space that you can use. So very nice. And you can see here the shell has this area used, and then the LSMem process has the other one, memory area used. You don't see the other parts because the other processes, like the file systems, because they have been started from the ROM. They are in a different memory setup. In that 8296 PET, you can swap out the upper 32K of memory with 2 banks of 32K each, and in one bank this is basically the user program space, and in the other bank that's the system program space where the other programs are running. So for example, in the CSA architecture that you that was the original one, you would actually not see much here, because most of that would be basically not usable, because the task only sees that amount of memory that is being assigned, and if the task doesn't need that one, it only get that much memory. It only gets assigned 4K, 8K, something. It can extend that, but that's it. And you would only see in the memory mapping, you would only see its own memory, but not the memory of the other processes. It's only in those shared memory architectures like the PET or the Commodore 64, you can actually see multiple tasks here. Another nice feature, you can do piping. So when I show the directory and then pipe it into the word count utility, you can see, and now actually I'm going to cheat a little because I'm going to do an alt warp. Whoops, there it is. It counts the lines, the words, and the characters of the output of that command and prints it. And there's some upcoming feature. If I do that again, so I need to be looking at where the disk drive is, because there's some kind of situation that might not be. There's some, so I can do a control Z, which is in device mapping, it's page down and Z, because page down is actually the repeat key, because the Commodore PETs don't have a control key. The repeat key of the business keyboard of the Commodore PET, which is the 8296, uses the business keyboard, has a repeat key. This is doubling as a control key, and then I use control Z, and then I can put that. I can break out of those programs, and I can see they are still there. You can see they're all here. They're all running. You can see that this is the shell that is here actually running here. It's suspended while the child process is running. It waits for a signal that either a child process has died or it has gotten back its kind of foreground shell. What you can do is you can do a background 0, or better foreground 0, and then the other process is coming back again. And now don't ask me why it's counting something different. Yeah, okay. Maybe I stopped it somewhere in the background, but I don't know. Interesting. So because now the numbers are different. So the ls, I must have stopped the ls somewhere in the middle of it, but it worked before. But you know, demo is demo, and demo goats have not been good to me in this case. I'll have a look into that at some point. This is actually a feature that is in the upcoming 2.2, so there's still some stuff to be ironed out. Now, how do you start another program on another console? There's a specific program. It's called OnTTY. That you just give it the console you want the other program to run on, and then the program to actually run. And when it comes back, it takes a moment to load. OnTTY is loaded. You may have seen the blinking of the red light, because OnTTY's own program loaded from disk, and then now it's loading the shell from disk. So just let me warp that a little bit. Okay, here we are. When I do a PS, again warping. It's very nice actually. You can see we have the original programs we had before. We have our shell, we have the PS program that I'm running here, and we have the other shell, and then we go to the next console, which is the old shell, and then we have a new shell. So you can just as well that's how you run another shell in another console. So you've seen there is some redirection, so some piping between commands, and there are a couple of other tools that are available, like hex dump and stuff like that. So but there's also redirection. So sorry, this way around. I can write something to a file with an echo command, and by piping it into a file, and then I can just call that file, display that file with the cat command, and then it should come up and show the content. And of course I can do all stuff like that. And that's all available. Of course, now it has to read and load 3 files, like the cat command, the hex dump command, and then do the file. But here we are. That's hex dump and output redirection. You can look at the docs. You can also output redirect standard error and standard in and so on. It's all there. So now we've seen how we can start programs and run them, and how do we program that? So you do low-level programming. So you can use a kernel call, or you can use lib6502 level programming, which has a more standardized interface, and it kind of abstracts the kernel interface away, which is actually more stable than the kernel interface at the moment, because I'm doing some major refactoring on the kernel right now. So the binaries are compatible across supported architecture. So you can build a binary, you can run it on the Commodore 64, you can run the exact same binary on the PET, you can run it on the CSA in any kind of memory architecture, because it's using the relocatable file format and late binding for kernel in lib6502, and that makes that happen. So looking at the documentation and where you get the source code is all in a GitHub repository of mine. Link is in the description below. You have different folders here. Apps is for the applications, architecture is for the specific architectures like the Commodore 64 and so on that are supported. There are some that are more or less prototype or sample for embedded, and one for a single board computer of mine, but those are not really maintained are the Commodore 64, the CSA, the PET 32K, and here the CBM 8296. And for all of those, you have different files that are needed to build the kernel, configuration, stuff like that. Most important for you would probably be the boot folder, where actually in the end there is this OSA D64 image that contains basically the binary of the program. So looking at the documentation, so there's devices. You can see some generic ones. Those are generic devices that can be included into multiple architectures depending on configuration. There's some SCSI code in there, which is basically not integrated yet. I see just now. Well, okay, let's go back. Let's go to the doc. The doc is in ASCII doc format, and you can browse it here, and you go here and where is this? And for example, if you want to run, let's look. If you want to go to kernel documentation, there's a folder for the kernel documentation. Every kernel call is documented here. Like for example, the semaphore code, free a semaphore. You give it a semaphore number. What is the return in the error situation, and you have the counterpart, which is PSEM2. PSEM2 is actually different from the original PSEM because I changed the semantic. This was the only one where when the carry was cleared, it was blocking. All other calls that had the option to block or not block had carry set to block, so I changed that. So that is one of the API breaking changes in 2.2. But anyway, you can see here everything is documented as it should be. Then so there's you have priorities. You can do a renice call to the kernel. sbreak is to increase the memory, which is only really relevant on MMU based systems, and so on. Get info is the call. It's also a it's actually get info 2 is actually also breaking change, because I had to bring in all the thread information now in the latest release. So there are some general documents, like if you go here, there's a kernel information that gives you an overview on the kernel interface description, and then you can link. It links to the to all the other code, which is actually interesting that I still have the I still have the absolute address there, which is from release 1. So let me quickly note that kernel 7.8 doc contains absolute kernel call addresses. Okay, milestone. This should be the next milestone, and there we go. Okay, so that'll be fixed soon. There is for every port there is a description. So you have a port for the Commodore 64. How the booting, the build works, the booting, included programs, and so on. What the memory map looks like. What semaphores are there, because you can run, for example, the IEC and the parallel IEEE 488 bus in parallel, but they both need a timer, and therefore they actually internally use a semaphore. When they need the timer, they ask the kernel to get a semaphore for that timer. Okay, so because we've been doing the 8296, you can basically see what the memory map looks like here. You have this memory map from the top here. There's the kernel in both banks. Then we have in RAM 1, we have all the system memory. We have the actual I/O, which is invisible in the user space. You may have wondered before when you looked at the output of the LSMEM. Then we have the virtual screens that are swapped in and out with the real screen. And that memory, the lowest 32K in the second bank is not used because it's actually the same as this one. There's the shared library. The library is re-entrant. You can use it. It's thread safe. There is a remnant from GeckOS 1.0 which is going to go away with a later version soon. Stack and zero page, as in the memory, as in the shared memory. Mapping like the Commodore 64, and there you can see you have all that space here for libc 6502 applications, which is nice. One thing I would like to show is this one. There actually is a TCP/IP implementation based on SLIP, Zero Line Internet Protocol. It's very experimental, but it works to a certain degree. I actually used to have a web server on the internet, which was Commodore 64, c64.rheinneckar.de on a Commodore 64 and an unmodified 1541. It was so horribly slow, but well, it was a proof of concept and it worked. Yeah, and let's see if we can try that out. So what I have here is I have the Commodore 64 loading the operating system. Once GeckOS starts in a specific configuration as is documented, it creates a process, a link, virtual terminal temp vice ser, and then you can run this little shell script that I built to configure that process that as a zero line IP connection with SL attach, and I'm also using the -L. You can actually dump all the programs. So, but we actually have to start that. And what we see here is, if we go to the now this is also true driver emulation, and you could probably see why. One of the first things I did with my Commodore 64, I gave it an IEEE 488 interface, which is much faster than the serial interface. You can see the benchmark in one of my previous videos. There is a SAR1 device. So what I can do is I can run the slip daemon on SAR1, and I should actually probably TTY. So I'm putting that onto the second video console, which is also Shift Tab. There are multiple consoles, and let's wait for it. Okay, here we are. You can see on the next screen the different modules inside the slip process are initialized. It all automatically starts an echo, discard, or chargen port. It has an HTTP server at port 80. You can do a remote login, and you can use lib6502 programs that use the sockets feature of lib6502. For example, to telnet out. But let's first have a look and see how this is working. I'll open a new shell, and first of all I'll do a ping, and the address, the default address is 192.168.0.64, and bang, we got the ping. Now we can do a telnet to the chargen port, and there you go. You get the correct. How do I actually stop that? I should have tested that. Wait. Can I do Control C? Uh-oh. Okay, I should probably kill that if that actually works. It doesn't. So let me close the terminal. I should have tested that before, of course. Okay. So okay, we are still here. Okay. So what we can actually do a telnet. Actually, we cannot, because there's not enough space in memory of the system to run another shell. Because if I do an lsmem, you can see there is the original shell is running. Then 2 is the lsmem. It's here and here. By the way, those close to 2 blocks of memory that are always a separate block that I showed that showed up in the 8296 try that we did. This is basically the memory that the lib6502 uses for each task. So, but number 1 here, slip D, bang, you get a lot of. It's just taking up a lot of memory in there, and there is no other way to do another shell. What we can do is, there are smaller versions of the slip daemon that only provide specific specific functionality, and you can actually use that there. So, but what I can show you here is if I telnet to port 80, and then I do get index.html return, and then you can see the floppy started working, and you get something from the disk drive. Isn't that cool? And yeah, it's slow, but it's a 1 megahertz machine. What do you expect? So what are the future plans? One glimpse you've seen is the controlling terminal. You can do Control-C and do some job control from the shell. You can put task in foreground and background and so on. That will be in the upcoming release 2.2. And then there is this little remnant of GeckOS version 1, which is a send-receive buffer that is used for a couple of things, which is on a fixed address in memory. So typically it's page 2. Yeah, this needs to go away to make it even more flexible and get rid of a semaphore that in some rare cases causes the system to block, because one task wants to get that buffer to send something to a file system, to open a file, for example, send a command to a file system. You use that buffer, and another one is doing that, and something happens and whatever, and that's something that needs to go away. And also the idea is to use a buffer-based approach. Currently streams are character-based, which is very slow. So which even makes the Commodore 64 load even slower than it already is. So the buffer-based approach, the goal is to achieve a zero copy load in memory mapped systems like the Commodore 64. So the file system directly writes to the area address space where it actually should end up. There's some kind of lookup process that where hard-coded IDs can be replaced with a lookup system. For example, the device file system could be replaced with that one, or the drives could get names. Also, I might be looking into some kind of terminal multiplexer, like and more terminal features, like more versatile addressing of characters in there, but that's relatively independent. And of course, more architectures. The Commodore 128 is definitely a target, especially as it has its, I believe, man, the Commodore 128 gets 40 next year, so that's definitely a plan to have that supported at that point. And of course, my extended micro and ultra pet architecture as well. Apple II will be a kind of challenge because the Apple II does not have a timer interrupt. Not even a screen retrace interrupt. I really wonder how they could build a system like that, but probably finding a way. It's way back on my to-do list, but it's on my to-do list. So, resources. If you want to look at a bit more deeper into that, here are the addresses. You can have a documentation on my webpage, but the actual source code is on GitHub. There's some more online HTML documentation, which Tenbe, which is Glenn Holmer, has done. He has done a talk a couple of years ago, and did some work on that. He actually has contributed the kill command to send signals to specific tasks. So yeah, I hope you like it. That's it for today. See you next time.